don't have it here. But remember that the specific heat of water is 1 calorie per gram degree C, which in English means that it takes 1 calorie to raise 1 gram of water 1 degree C. So you have to spend 1 calorie of energy if you want 1 gram of water to go up by 1 degree. In this case, we have not 1 gram, but 883 grams. And we're not raising it 1 degree, we're raising it 22 minus 4, or 18 degrees. Okay? So we've got 883 grams of water that we're raising 18 degrees. So the change in temperature, this is a Greek letter delta, or we might call it a triangle, but that stands for the change in something. The change in temperature is 18 degrees. All right, so if we're changing the temperature by 18 degrees, and rather than 1 gram, we've got 883 grams, that means that the total heat is 883 grams times 18 degrees C. And then we actually have to multiply this by the specific heat. So you've got the mass here, you've got the change in temperature here, and then the last term is the specific heat. So in this case, that's 1. Notice what happens with the units here. Grams and degrees C cancel because the ones over here are on the bottom. So cancel, 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 and we're left with calories. Somebody have a phone handy?
15, 894.
And that's in calories, little c calories.
Why do we cancel grams and centigrade? I thought it cancel centigrade and centigrade. How does it come about that we cancel with the grams?
Grams here, and then grams on the bottom of the specific heat. So this is a weird unit. It actually has 2 different units on the bottom and then 1 on top. It's calories per gram per degrees Celsius. It's got extra stuff in there. Don't worry too much about that, because that number is pretty much always 1. So you could mostly just multiply the mass by the change in temperature. When would that be different? When would you have to worry about that? Yeah, if it's something else. If it's something that's not water. Other things are going to have different specific heats. In fact, let's take a look at that. I think I've got a table somewhere here. Nope. Nope. Maybe not. Okay. I will find it. Let's pull up our book. Here we go. Okay, let's look at, sorry, thought I had that more readily available. Here are some other specific heats, table from the book. So you see water down here, liquid water is at 1. And remember the sentence that we said, remember how we described this. The specific heat tells us that it takes 1 calorie to raise 1 gram, 1 degree C. So you got 1 gram of water, and you want it to go from 22 to 23 degrees C, that's 1 calorie. Notice that pretty much everything else on this list, and that's true for most materials, has a lower specific heat than water. So what does that mean? What does it mean that something has a lower specific heat than water? Mm-hmm.
Less calorie heat.
Yeah, exactly. It takes less energy to heat something to the same temperature. So to heat aluminum to the same temperature as water, if they start at the same place, would take a lot less energy. And we kind of experience this. Have you ever heated aluminum in some way, like aluminum foil or an aluminum pan? What happens when you put aluminum foil on top of a hot piece of food? It's hot, right? Yeah. You wrap your hot food in aluminum foil. The aluminum foil gets pretty hot pretty fast. What happens if you put your hot food in water? Does the water get hot really fast? Not really, right? Kind of actually might cool down. Well, that's an issue of the specific heat. So aluminum has just a fraction of the specific heat of water. A fifth of the specific heat of water. And that means it takes a lot less energy to heat that aluminum up than it does to heat that water up to the same temperature. When we do these kinds of calculations, these kinds of experiments like we did in the lab, we're usually always using water. So that's why I say I want you to be able to understand specific heat, understand what it means, and kind of think about the idea that it takes more or less energy to heat something to the same temperature. But in terms of actually doing the calculations, you can just think of it as the mass times the change in temperature, because that's usually what it'll be. The specific heat will usually be 1. Let's see what specific heat means in our energy curve. So remember our heating curve for water? Last week we talked about, you did some activities about that where it was heating at different points. This one actually isn't a great example because it's not to scale. Let me pull up the other one from the book here. All right, so here's the heating curve for water, more to scale. You've got heat absorbed on the x-axis and then temperature. So as we're adding heat, we're increasing temperature until we get to the phase changes, melting and boiling, where it flattens out. What does it mean that this line, heating up ice, is steeper than this line, heating up liquid water?
Does that mean that it's changing into something?
Well, yeah, the phase change happens right here as it melts. Yep. So you're getting a phase change right up here, and there's a difference in those two phases. But the slope of the line itself, the fact that this one's really steep and this one's less steep, what does that mean?
It needs less time. Like when you start heating up, it needs more time to heat up. Like
Right.
Get more energy and more.
Right, exactly. So the one that is shallower over here means it needs more of this energy to get to the same temperature as this one. All right, and that's another way of talking about specific heat, like we were just saying. If it takes more energy to heat something to the same temperature, then that thing has a higher specific heat. In this case, the liquid water, has a higher specific heat than ice. And we see that in the numbers too. Ice, solid water, has about half the specific heat of liquid water, which means you can heat up ice with less energy than you can heat up water. Oh, we forgot one thing about our problem, so let's go back to here. So we got our answer in calories, but that's not what the question asks, right? What does the question ask for kilojoules? How do we convert calories to kilojoules? We need a number, right? We need a conversion factor. Yeah, that is the number. You don't actually have to memorize this number, but it'll be helpful if you've done a lot of problems with it. That 1 calorie is the same as 4.184 joules. All right, so how do we use that information? Oops, I'm putting our units here. We do a regular old conversion just like in the last chapter. So we get calories on the bottom and joules on the top. But that's, again, that's still not our answer, right? We need one more, because we're asked for kilojoules. So we need to cancel out our joules and end up with kilojoules. So how many calories in a joule? We just wrote that down, right? 1 calorie is 4.184 joules. And then how many joules in a kilojoule? 1,000. That's one that we need to remember. There's 1,000 of anything in a kilo of anything. So to solve this, we're going to multiply 15,894 by 4.184, divide by 1,000. And what do we get? Anybody have a calculator handy? Anybody check that? Is that right? What did you get? Looks about right, because we're multiplying this by 4 and then dividing by 1,000, thereabouts. So that's the answer here, right? That's how much energy is absorbed by that water cooling to room temperature, or warming to room temperature. So there's really only two kind of math things to worry about in this chapter. One is these kinds of problems where you multiply the mass times the change in temperature, and you can practice that a little bit when you finish your lab also, because it'll ask you to do that. And then the second is just more unit conversions, just with different kinds of units. Calories and kilojoules instead of all the other stuff we've been dealing with, grams, pounds, all of that. But the procedure for that conversion is the same. Questions so far on this kind of stuff? Looks good? Maybe? Maybe a little? All right. Now, we didn't talk about temperature conversions yet, right? I think we maybe missed that. Yeah, I'm pretty sure we skipped over that. So let's do that. First thing to note, temperature is different from heat. Heat, when we talk about heat, we're talking about energy, which means we're talking about calories and joules, and maybe BTUs, some other weird units, therms, depending on what system you're in. Temperature, we're talking about measuring average kinetic energy of molecules. And what are the units we usually use for temperature? Yeah, degree Fahrenheit, degrees Celsius, and Kelvin. We can write those words if you don't know them. Fahrenheit, whoops, spelled that one wrong, Celsius, and Kelvin, all named after people. So let's take a look at these three scales. I think we can best do that with a picture. I'll grab another picture from our book here. Put this over here. On the left, we've got Kelvin, and then Celsius, and then Fahrenheit thermometers. And they're lined up so that the same temperature is in the same place. The top line, I don't know if you can read that, top line says boiling point of water. So boiling point of water on the Fahrenheit scale is 212, on the Celsius scale is 100, and on the Kelvin scale is 373. Normal body temperature, we've got 98.6 Fahrenheit, 37 Celsius, and 310 Kelvin. And then freezing point of water, 273 Kelvin, 0 degrees C, and 32 degrees Fahrenheit. So you see they're all kind of at the same place there. Notice the thing that's confusing about these units is that they're a little bit different from the conversions we've done so far. All the other conversions are what we would call factor conversions. So we multiply something by a certain number, and then we have another unit. Right? You multiply calories by 4.184, and you've got joules. You multiply what do I say? You multiply gallons by 3.8 and you've got liters. There's a bunch of them. You don't have to remember them, but those are the types of things we've done. We set up those big strings of conversions to do whatever. That doesn't work that way with temperature. The reason it doesn't work that way with temperature is because there is an additive component also, meaning we have to add or subtract instead of just multiply to get things to the 0 point. And that screws up that whole idea of setting up all the factors when you have to add or subtract. So the best way to do this is to actually remember some different equations. And I'm going to show you how we do that. Notice that between the freezing point of water and the boiling point of water, there are 100 Celsius degrees, 0 to 100, and there are also 100 kelvins, from 273 to 373. Another weird thing is that Celsius and Fahrenheit are noted in degrees. We've got degrees Celsius or degrees Fahrenheit, but Kelvin is a unit, like a gram. So we talk about kelvins rather than degrees Kelvin. So these two have 100 degrees separating the boiling point and melting point of water, whereas Fahrenheit has 180 degrees. So what's bigger, a Celsius degree or a Fahrenheit degree? Is bigger? Careful. Yes, each Celsius degree is bigger because there's fewer of them between the 2 points. So a Fahrenheit degree is a smaller degree. So we have to convert those. We have to make the degree size change. But we also have to change the offset because they don't all start at 0. Celsius, yeah? Mm-hmm.
Degrees Celsius there.
Right.
Celsius, and then Kelvin is 100, and Fahrenheit is 180. So.
Yeah, that's the number of separations between the melting point and the freezing point, or the boiling point. Yeah, the freezing point or melting point and the boiling point. You're going from 273 to 373. That's 100 separations, 100 gradations. In Fahrenheit, you're going from 32 to 212, which is 180. So it's like you're splitting it up into 100 pieces, or you're splitting it up into 180 pieces. If you split it up into 180 pieces, each piece is smaller. And then we've got this weird offset because Celsius, freezing point of water, is 0, but Kelvin it's 273, and Fahrenheit it's 32. So it's not just multiplying, it's also adding and subtracting. Now, why do we do this? These two scales are just because they were used in different parts of the world. But Celsius and Kelvin have the same scale, they're just off by a certain number. Why are they off by a certain number? You know? Why have both scales if one is the same as the other, just offset?
Universal.
What do you mean?
Like instead of guessing Fahrenheit and Celsius, we use one way of measuring it.
All right, well, but why not pick one of the other ones? Okay, I'm not sure it was necessarily newer. I don't know. But yeah, okay, I get that, yeah. Did you want to say something about that too?
Well, they have the different point of, like the point of freezing.
Yeah.
From Kelvin, it's 273, so they declared that one as freezing point.
Right.
So,
But why 273? Anybody know where that comes from? Standard point? Yeah, it kind of goes, it depends on where your reference point is. The point of the Kelvin scale is that in Kelvin, there is no below 0. So in the Kelvin scale, 0 is the coldest you can possibly be. It's when molecular motion stops entirely. And if something is entirely stopped, it can't move less than being stopped, right? So in the Kelvin scale, 0 is the absolute floor. It's called absolute 0, and you can't go below that. That is the coldest you could possibly be, absolute 0. That's fine, but it makes it a little bit more cumbersome to use at everyday temperatures, because absolute 0 is 273 degrees below the freezing point of water. So you're talking about temperatures that we never experience. We never deal with those kinds of temperatures. So a Celsius or Fahrenheit scale makes more sense dated because the temperatures are something we commonly experience. So that's the difference between these two, which means that our first conversion from Kelvin to Celsius is actually going to be the easiest one. If we want to know what a temperature, here, let's do it this way. A temperature in Kelvin, we'll write it T with a K, is just the temperature in Celsius plus 273. So whatever your Celsius temperature is, you add 273, you've got Kelvin. And it goes backwards pretty easily too. The temperature in degrees C is the Kelvin temperature minus 273. So why use Kelvin in the lab or anything like that? It's not just when we're dealing with really cold things. It turns out that as a unit, Kelvins are useful because they start at 0. And so you can use them in certain types of equations and calculations that you wouldn't be able to use Celsius in. So that's where that kind of comes up. Now the other two. The other two require an offset because they're 32 degrees apart. And then also, so we have to kind of slide the scales like this. And then we also need a multiplication of something to account for the fact that the degrees are different sizes. So these equations get a little bit trickier. So first we'll use the temperature in Fahrenheit. If we want to solve for the temperature in Fahrenheit from the temperature in Celsius, we take the temperature in Celsius we multiply it by 1.8, and then we subtract, or we add 32. And I always get these mixed up, so let me make sure I'm right with this. For some reason, this is something that always messes up my head. Yeah, that's right. Okay. So the temperature in Fahrenheit, and remember your order of operations from math. You have to do the multiplication first before you add the 32, or it doesn't work. So make sure when you're typing this out, many modern calculators like scientific calculators, graphing calculators, will do this automatically. So if you type something times something plus 32, they'll make sure to do the multiplication first. But if you have a simpler calculator or some other thing, I don't know, it may not do that. So make sure you do that multiplication first and then add the 32. To go the other way, we have to do the opposite. So if we have Fahrenheit degrees and we want Celsius degrees, we take our Fahrenheit degree and we subtract 32, and then we divide that whole thing by 1.8. So in that case, you have to do the subtraction before you do the division to get it to work. All right. So those are the equations. There's not really any shortcut to that. That's just how it's done. We just have to remember some of these numbers. I will say the biggest error here seems to be that order of operations issue. People always forget, including me, which you do first, then divide by what. So what I do to check myself if I need to do this to convert some temperatures is I remember some basic, I guess you could say, landmarks in the temperature scale. I remember that the freezing point of water is 32 degrees F, 0 degrees C, and 273 K. I remember that body temperature is 98.6 F, 37 C, and 310 K. I guess I didn't remember that one. And I do remember that boiling is 212 F, 100C, and 373K. So that way, if I'm doing these equations and I don't remember which one's which, I write them down and I try one and I see if I got that number that I know. So if I know that 0 degrees C is 32F, I know that. I just remember that. I know both freezing points. Then I can write down these equations, try them both with 0 and 32, and see which one gives me the right answer. So if I forget how it goes or forget which one's which, I can still kind of figure it out by having some numbers that I remember. And then kelvins are always way higher than everything else. Unless we're dealing with super low temperatures, you're always in the hundreds, 200s, 300s in Kelvin. So if you end up with small numbers in Kelvin and you're not talking about something that's super, super cold, probably there's a mistake there too. All right. So any questions with temperature conversions, or should we try some? What? No? You good? Okay. Let's try some. Has anybody ever had an issue with temperature conversions, like with cooking, where you have a cookbook from one place or another place that's different from how your oven is set? That happens sometimes. So you got a this is kind of an interesting question. So you've got somebody comes to your house and they're going to cook, and they've got their cookbook and they're ready to put the thing in the oven, and they heat the oven to 175 degrees Fahrenheit because that's what it says in the cookbook. Is that a general oven cooking temperature that we use for those of you who cook? No. What's wrong with it? It's pretty low. You're not going to cook much at 175, right? You might make some nice bacteria-laden stuff, but you're not really going to cook anything. So what probably happened? Why did this person who came to your house set your oven at 175?
Maybe his own house is not
Right. So whoever came over to cook thought, I always set my oven at home to 175 in Europe or something. So really, what this person meant was 175 degrees C. But your oven's in Fahrenheit, so let's convert 175 degrees C to Fahrenheit and see what you come up with. So try to punch out the numbers on your phone or something, see what you get. And let's make sure we can all get these conversions. What do you get? 347. Anybody get something different? Other numbers that you got? Everybody got that? Nobody got anything different? You sure? All right. Yeah, so I think that looks right. So really, you should bake this thing around 350, right? Is what you should set your Fahrenheit oven to. The nice thing about temperature conversions is we all have some experience with temperature. So if you get some number that's wildly different, you can probably figure that out. If you know that water boils at 100 degrees C, which you should know, or you should at least know now, you should memorize that for this class, then you know that if it's 175 degrees C, it's got to be well above the boiling point. So if you do this calculation wrong, like if you plug this into this one instead, you're going to end up with a really low number. You're going to end up with like 80-something. And you know that 80 something is not, in Fahrenheit, is not way above the boiling point of water. So you must have done the conversion wrong. You can go back, try again with the other equation. Just like with the energy stuff, just like everything else, it's always a good idea with unit conversions also. It's always a good idea to think about whether or not this is a reasonable conversion. Right? They should be around the same thing. If you're converting centimeters to inches, you know a centimeter is smaller than an inch, not wildly smaller, but about half the size of an inch. So if you've got 100 centimeters and you convert it to inches and you get 2 inches, you know that's not right, and you can go back and check it. Always got to think about it. It's not just about plugging in the equation, it's about thinking about what's reasonable. All right, so any questions about the heat stuff, the energy stuff, the conversions? Thinking about it? How's the lab coming? Did you get most of the questions done? Yet? Not yet? Okay, keep working on those. Let me know if you have questions. So we're going to move on now to the next topic, which is atomic structure. I have another short activity for you. I know we didn't quite finish the last one, but we took care of it talking about it up here. So I'm going to stop talking for a little bit and let you work on this one. This one's a little bit different from the last one in that it has pictures. Well, the other one had a graph. I guess it's kind of a picture. So reform your groups of, let's see, how many people do we have here? Oh, we have all even groups again. So we can do groups of 3. Once again, you don't have to keep the same groups. Try different groups if you like. Now when you get together in the group, first thing to do is tear off the front sheet. Tear that off. There are no questions on the front sheet, but the front sheet is the model that you're using to answer the next questions. And like before, this doesn't look very groupy to me. It's the groups going. It can be done together. 3, yeah, 3s, however you want to do 3s. Go for it. All right, almost there. One more group to make. Jumping over again. Thank you. Okay, so tear off the first paper, and you're going to use those pictures to answer the other questions. Now, a couple of things to note about this, so you don't get confused. Like the other thing we did last week, this is not meant to draw on your prior knowledge, extensive as it may be, though you don't have to pretend that you don't know things. But you should be able to answer the questions based on what's in this packet. They may even seem a little easy for a lot of it. The other thing, I don't know why it's done like this, but the symbols, there's only a very slight difference between these two. There's like a little shadow on that one. So try to read that as best you can. But yeah, it should have been a little bit more clear. Anyway, so look at these models and try to answer those questions as you can. When it comes to the point where you need a periodic table, you can certainly use this one, but you probably are going to want one with the names on it. So hopefully someone in each group has at least a book or a lab notebook or something with a periodic table with the names on it. If you don't, I probably have some up here. So just let me know.
First 300.
They may need one. What do we got?
This number will call, this is the atomic, the bad, not the point number.
Right.
Six. That's six protons. No. Yeah, I think that's right. Yeah, it's just the number of protons. I think it's the protons and the electrons because the neutrons don't. It's just the neutrons. What do you guys have? The alpha number is just the number of protons. Hydrogen, atomic number is one because it's an alpha. For what? We're talking about we're talking about
Right, but how many protons?
right, 17. All four atoms will have 17.
Yeah. Well, what do you think?
Yeah.
So you got 4 different hydrogen atoms, 3 different carbon atoms.
It's in all, so
What?
any of those things. I forgot what K used.
What? How many protons are in, like, for all the hydrogen atoms?
That's in my thing. All those.
Adding all
atoms.
these up.
No, yeah.
Always have 19.
In each one.
It has a different number of protons.
So what about carbon?
They can have a different number of electrons
So then how do you
than protons.
Always
Always have
The
same number. I need to get
It's supposed
So
to be.
many, like,
Right.
because there's so many
I mean, at
numbers.
this point it is, because what you see here is some different examples, and then kind of use that to come to the next conclusion.
Okay. I understand how it's supposed to.
The atomic mass is the protons and the electrons. The total number, both.
What do you think, based on what you see here?
I'm just trying to remember.
Much better remember, just look there.
I'm counting.
Alright.
Yeah, zero.
Well, sure, but what is the significance based on the part? How does it have different numbers of particles?
Which question? I mean, it could be. Yeah. Yeah. Plus, so
So here you've got. You've got hydrogen plus. Here's hydrogen Right. So,
Yeah.
what about?
So I think for hydrogen.
Right.
No, it's neutral because the electron, you can share the electron.
Oh, no, the other two, the 13. A little bit, yeah.
This one
Yeah, same proton, same neutron. Right. Right, so this one has one more electron. So then think about what's going on with this one here, or here. Idea of what this is.
So do we just write it plus and
So you wanted 8 or 70 because it's the total number of protons and neutrons for element plus the isomer, or whatever it's called, which is the same element but has a different amount of neutrons. So it takes together all of those and that's the total. Okay, so it's like all the protons and the neutrons, all of the different isomers, or whatever it's called, hydrogen, right? It's all of those different ones put together in one. I think that's the gas.
Okay, so G is going to be
And then what is this one? What is that neutrons? Use
Oh, okay. So I think it's asking to the right of the symbols, it's talking about Ds, plus, minus, yeah. What does that mean? So compare those with the similar one, like hydrogen 1 plus versus hydrogen 1, that, and 13C minus versus 13C. You don't think about what's different. It's not that, look at the numbers of the part. Which ones are you looking at? Look at the hydrogen one first. So you got hydrogen plus and hydrogen neutral. What's the difference in those two? Yeah, they each have one proton. Right, but you see any major differences in the pictures? Right, so what is the little circle?
I sworn I knew the number of electrons.
Okay, you got the carbons. So you got 13C, you got 13C minus. What's the difference between those two?
Oh,
Yeah, that one is different. That one's a little different. What about the numbers of electrons?
pretty sure yeah, because the number next to it shouldn't matter. It's a small number.
You have to do yeah.
But that's the number.
So that plus or minus must have something to do with the number.
It doesn't matter. It matters.
What does that say? So check it at the bottom. You got magnesium.
No, it's not the
24
number.
neutral versus
But that's what this is.
it's 2.
Yeah.
What's the difference?
The mass is,
The one.
yeah, it's the one that's like 20.
Right.
Whatever. Yeah.
So whatever it's doing. So that doesn't change.
So what does that have to do with
mass.
the electrons? How are the electrons plus 2? What is it?
So this is the answer.
Did you know?
Which total? Which one's the last one?
So what's the difference between 10 and 12?
It says
Plus 2.
It's all, it's just present. Oh, no way. 12, 13, they have different.
So you come up with a rule
I think
about what
carbon
always
12 and
has to
13,
be.
they might have a different number of neutrons.
So instead of saying.
But yeah, sorry, what mass is all part of the same mass, so whatever the mass is.
In a box?
Same particles are here.
Yes, it's no, like for speed.
Yeah.
This one's at the atoms.
They should have the same.
Yeah, that's right.
The same, the same.
So it's also known as the atomic weight.
What structural elements?
I think the mass numbers are based on what you.
It's always the same.
It adds up to the proteins.
Yeah.
Awesome. No, because they're different.
For one mass.
No, and it just looks at that. I think you would look at that and then we'll look at that. And then
Yeah.
you subtract.
So there you go.
They
I mean, like, the mass is the
Alright.
same.
Yeah, because.
I guess, no, they would wait.
So you decided that in the previous questions that,
But you're comparing like carbon 12 and carbon
protons,
13.
the protons outside the
Carbon 12.
And then this is basically.
yeah.
So you would have
If
to.
they have more than 17, it would be tornadoes. So the atomic number, the number of protons, determines the atom. The number of neutrons seems to have something to do with that number on the left-hand side. Right, because if you go from like 12 to 13, it's the neutron that changes. So the charge then has to do with the electrons. Protons are positively charged, electrons are negatively
Yeah.
charged. So if you have the same number
Yeah,
of
it's a neat number.
protons and electrons, positives and negatives balance out. It's zero. If you have more protons than electrons, then you go more positive. So that's what the plus is, plus 1, plus 2. If you have more electrons, it's going to go negative. Minus 1.
So.
Right. So you can determine what the charge is going to be based on how many electrons there are relative to the protons. So if the protons plus the electrons add up to, protons minus the electrons add up to, gives you that.
So the difference between.
Right, well, let's you've got, in all these cases, number of protons choosing as opposed to n. That's whether it's basically there's an inflection, right? So that's well, careful which numbers you're talking about. When you talk about protons and neutrons, you're that that's still neutrons, but the neutrons plus the protons are just so it's the electrons whose number is negative More electrons.
Yes.
Negative charge. That's what's
Yeah. And
sense.
right? Yeah.
Yeah, so what's the difference between the mass number and the atomic weight?
I was saying, if
This number isn't
you just
exactly
have
the
the,
same.
like, these are atomic mass,
It's
compared to the gases, then
It's actually the opposite.
actually probably would be.
Kind of, yeah. Yeah. Let's talk about that all together, actually. Okay, let's see. Oh, no, let's just talk about that one.
Oh, okay.
So one thing that comes up, let's all talk about this for a second, in the second page?
Yeah, number
At
8.
the very, very top of the second page, it's talking about atomic mass numbers. And it gives you these different examples. What's the mass number for the following atoms? So we've got these numbers specified, but then if you look back to the original thing, it's kind of confusing about what the mass number is, because there's these numbers up here like that, and these numbers up here are clearly what? What leads to like this 13? How can you find that? Not quite, but yeah.
It's the number of protons and neutrons.
Right, the number of protons, the number of neutrons give you this. And that's in fact called the mass number, or the atomic weight. Then what accounts for this number with all these decimal places, or the numbers on the periodic tables that are all kind of weird decimal numbers? Part of it is because the electrons have a tiny bit of mass to add to that. That's part of it. Look at, well, that's actually, look at what's happening over here in carbon. So carbon has 6 protons, 6 neutrons, and 6 electrons, and is exactly 12. Like 12.000000. Idea why that is? Why it's different from the other ones? It's actually just set that way. It's just arbitrary. We decided carbon was 12 because it had 6 protons and 6 neutrons. So we just set it to 12, and then we adjusted everything else accordingly, even though it doesn't exactly work out that way in real life. So that's why there's some decimal places here. Some other things get a little weirder. So in this case, let's look at chlorine. So this tells us it's chlorine 37. And chlorine has 17, is atomic number 17. So that means we've got 17 protons and 20 neutrons. Okay. 17 protons and neutrons. So then the mass number here is 37. But if you look up on the periodic table, or you look in your own periodic table, you see that the atomic weight of chlorine, the number on the bottom, is 35.4527. That's not even really close to 37. That's not even rounding error. What's happening there is that isotopes, the different masses of the same element, exist in nature. Chlorine, for instance, has 2 common isotopes in nature. Chlorine 35, which has 17 protons and 18 neutrons, and chlorine 37, which has 17 protons and 20 neutrons. So 2 different forms of chlorine exist in nature. If we could take little tiny atomic tweezers and pick out individual atoms of chlorine in a chlorine sample, we could pick out chlorine 35 and chlorine 37. We can't actually do that. We can only see chlorine in millions and billions and trillions of atoms at a time. So these numbers are averages of the isotopes. Chlorine has 35 and 37. 35 is more prevalent than 37, so the weighted average of the two comes out to 35.4 something. So if you're given the mass, by a particular specified isotope, then the mass number is what you see there. If we're just talking about a bulk sample, like in lab, then we use the masses on the periodic table.
I'm looking for another question that was asked here, forgetting what was said, also like that can chlorine have two different.
Yeah, this one, right? Number 5. Is that what you're talking about?
Yes, yes. Do you
Yeah.
think chlorine exists?
What do you think?
From the explanation, I think so.
Well, chlorine can exist with extra neutrons, but not extra protons, because what happens when you go to 18 protons? Anybody? It becomes something else. If it has 18 protons, it's not chlorine anymore, it's argon, the element next door. So every element is defined by its proton number. That's what we call it. However many protons it has, that's what we call it. And then the mass number can differ, that gives you isotopes, and the number of electrons can differ, that gives you ions. So if you're about there, you're almost through. Keep working on the rest of this packet. Try to finish it up, and then we'll take a little break. We'll come back and talk about it, and go on from there. Just 12. Sorry. Yes. Seems disappointed. Right. Yeah, because carbon in nature exists as carbon 12 and carbon 13. Mostly it's carbon 12, with a little bit of carbon 13 and a tiny bit of carbon 14. So you average all that together, you've got a little bit more than 12.
So it's like
Depends what I'm asking. If I say, what is the mass of carbon 12? It's 12. If I say, what is the atomic weight of carbon, unspecified just carbon, then it's 12.011. If the isotope is not specified, we use the averages from the period. Yeah. Yeah. We're almost there. Let's try to start.
This instrument, this is the way.
Right.
Why is it wrong?
Well, just regular easy. So, if, there's a positive hydrogen ion, right? Hydrogen ion. What's the significance of that? What is different about that? You don't really put it there. Right. So right there. So that would give you the number of neutrons. The mass number is all together. That would be.
Because it's asking for, it's 48. That's the rest of it.
The atomic number is, well, here. That's the mass number.
So like, here's number 19. And then that's 19. That's what that, yeah, that number just means that.
Yeah, subtract.
No idea.
Yeah, just as there are most elements left.
Well, yeah, it's something with a math.
Yeah.
So, let's take it.
Mass number minus.
Right. Do they have different? Different? Were they the same? So they're the same way. Yeah, look at the picture and see what's the same one. What are you looking at?
Subtract and like, find the top.
That's not
Wait, how do you get the rest of the pictures?
I thought that's what we said.
For which one?
The first one.
40.
No,
Yeah, it just specifies with the small number.
so that's
Yeah, that's always the same.
Yeah, but you're not supposed to look at the book. You're supposed to figure it out from what you've seen so far.
It's hard
So
to.
you saw what you figure out what you did. So you can. I don't care if you write the right answers on the sheet. Figure it out. That's good.
Yeah. Yeah.
All right, I know you said we were gonna finish this up, but it seems like everyone's sort of losing their mind. So let's take a break now, and we'll come back, keep working on it in about 15 minutes. And we'll talk. We'll come back. When we come back, we'll talk a little bit about the first part, and then we'll continue with the second part.
In each grade.
It's 2 in the first grade, and then 8 in the outer range, and that's the quality.
I just wanted to give you a heads up. I'm moving to next and I know that,
22nd.
yeah, and I know that's when we have our exam.
Yeah, so you're missing exam.
Yeah, so I don't know if I can make it up.
No, there's no makeup exams. But what can happen is that you can replace that exam with the final, with your final exam score. So whatever you get on the final will count double for that one also.
Okay, because I was
Will you be
like,
missing more labs then too?
I would just be missing
Oh,
that.
Okay.
So
So just miss
just,
the exam and the 2 classes.
yeah, so just the 22nd to the 26th because I will be visiting my grandma's.
Okay.
Just that.
Okay.
Just wanted to give you a heads up and I had to give my other professor a heads up. And
Right.
so the final exam would.
It will count also for that exam.
Can I get extra credit? Is there any possible way of earning extra credit?
No, there's, I mean, you can do more of the regular stuff, you know, just try to get better points on
And
other
then
stuff.
for homework wise, since I haven't really been here, I saw that you posted up stuff online. How does that work?
If you
Is it
want
not-
to do that,
Mhm.
you can. You have to buy a pass to that site, and you
And
can go through the
that's more
homework.
benefiting us, right? Like people who
Yeah,
are
and so you can get some points for that. That will be there's a homework component to the grade. There's your score on that. If you complete all the stuff. If you decide not to do it, it doesn't count against you, but you don't get any homework grades. And your grade is just for quizzes and exams.
Oh, okay.
Because we don't collect any homework.
But that would benefit.
I think so, yeah.
Okay. Okay. That way, because
If you keep up with it. So the first assignment is due this weekend. Sunday night.
yeah, because when I got the notification, oh, I just got leave.
Yeah.
Oh,
That's
okay.
good.
Okay. Thank you. So what is the second? What's the second?
P.
No.
I'm just going after what, it's the number of short lines. The fourth one is yeah. When you look at
The same location.
that's for all the math, 30.9.
The number
Yeah.
Yeah. Oh, so it's that.
Yeah. Okay, thanks. Yeah, just, so, everything is.
I don't know.
Wait, this could be a trick. This could be.
It could be,
Right, so that's what this probably says.
yeah.
So just like we did this. Yes, no, this is.
GM?
It's the same as.
Yeah, so we have more, has more
So
programs.
then it'll be easier, 18.
Yeah.
So,
That's 18, that's 18. Do you think that's
It would have-
the same as the electron?
Right.
Okay, so like I.
But that says neutrons 38, so we have 40.
this is 40.
Those two.
Yeah, okay. Wait, what? No, because of that. So neutrons are 38. So it's, it would just be 40 then.
Let's
because
just
it
do
only
this
has
first. We'll do the
38.
15 because the
Yeah,
number
yeah,
of protons is
it's
the
up.
exact same number. Right. The electrons can vary.
So where's the 15?
15, do we have 13?
Yeah.
15 plus 17. That's 48, and that's 32.
The atomic?
Okay, I'm sorry.
Why is it so hard?
It's a change.
And the mass.
It has mass atomic number of 15. And the same way it has a number.
Why is it saying not
30, yeah.
And then plus the electronics, you can add that too. Does that make sense?
It's very hard to become a number.
But how come when this one was two different numbers? Yeah.
Yeah. The mass is 81. Because I'm pretty sure if it's would be 81 to the algebra. Because the mass is different. He said this is just like the general line. Because this is 81, and we can be specific about the number next to element.
Yeah.
I'm sorry. Yeah. So, yeah. So here was supposed to start. This one, how is it going to be different? Oh, yeah. I was supposed to add those ones. No, but yeah, like, no, it's very different because these things like this is.
No, I don't. It's like
And also there's another one. So maybe
It's games.
yeah, so I think it's health rather than.
It's first class. So what do you say?
So I think this is what I'm doing, that's 32, that's what I think, because I think the 18 is just different. Non.
32 or 34?
Because it's gonna be almost 30, right? It's 32 because you add these two.
Okay.
The atomic mass of the end.
So we said the number was 30.
The what? Yeah.
It's really, it's expensive. So it's like.
So we figured it out with the number. How many protons would they have?
We have 30.
Does that make it 30 over here?
The atomic mass. The atomic number is 30. Or one. No.
I don't think
Yeah.
I.
No, it has 38 electrons.
Like we usually
It's the end
like the cheapest.
positive. It's 2. Would have 2 more than 38.
So we have to subtract 65.
I'm not sure about the math.
Mass is 8. No, it's really minus 7.
Yeah.
Yeah. This is what I was.
So it's 30, that's the same. How much 30?
Say what?
The number of electrons. So the electronic is going to be.
Yeah. And the proton is 30, right? It's just like it's weird.
And it's like.
How did you hear me? I remember. Sometimes it gets awkward though. Sometimes I feel like it's a little too much. Yes, I was barely slept just morning, so like. Yeah.
Because it has 38 neutrons positively charged. And just two. I'm just assuming that means it has 2 mole.
And it's supposed to say 36.
Number? Yeah, 'cause that's just what's the number out there. That's all. That's probably wrong. I just copied from you. Yeah, that's fine. You're probably right.
All right. Sorry, I need a sandwich. So, how's this going? Horribly?
Yeah.
Awesome. All right, let's talk about it for a second. So first of all, before we get into the actual stuff, this is supposed to be frustrating and annoying. Not because I don't like you, but because if you struggle through this and try to figure it out, and we've tested this and it really works. This stuff sticks better if you struggle with it and you figure it out. I could just sit here and talk about things, and then you would have to go home and struggle with it and figure it out anyway. So we might as well do that here while I'm here to help you and answer your questions. I really think that it's worthwhile. I've seen that it's worthwhile, that it works better to work through it like this rather than me just telling you some things and then you forgetting about it 5 minutes later and then having to go back to the book and figuring it out on your own. I think this stuff will stick for you better because of it. So let's look at a couple of these things before we move on to the end of the... So in review, what can we say about what atoms are made up of? Protons, neutrons, and electrons. How do you know how many protons an atom has?
The atomic one. Or you can count it.
I guess if it's a picture, you can count it. If you don't have a picture, which number you look at?
Right.
Top right, atomic number. That tells you the number of protons. How do you get the number of neutrons? Yeah. So you subtract the protons from the mass number because the mass number is the total of the protons and electrons. Sometimes that's tricky because if the mass number is specified, you have a particular number, like 40. It's a nice even number. That's the mass number. But if it's not given, then you have to use these decimal numbers, and sometimes it's hard to tell exactly how many neutrons. So you have to do some rounding to figure it out. All right, what about electrons? What does that have to do with anything? What are the electrons? I think everybody struggled with this a little bit about what to do with the electrons.
Same as the protons.
It's the same as the protons if what?
If it's not negative or positive.
If it's not negative or positive. So if it's just a neutral atom, then you got to have the same number of protons and electrons and going to balance out. So then what happens if they don't balance out? Then you have a charge, either a positive charge, which means what? More protons, or a negative charge, which is more electrons. Okay. Second part, we'll talk about the periodic table when you finish this. So continue on, try to fill in this table. Again, the tricky part about this table is sometimes the mass is specified, like here. So you got potassium 40, so the mass is exactly 40, so you can get exactly the number of protons and neutrons. Sometimes it's not, so you have to look at the periodic table and just do a little rounding and do your best guess. But actually, I think in this particular case, the only one where it's not given is this one, and then you're actually given the number of neutrons, so you can figure it out. So you shouldn't need to do any rounding with decimals on there. And then we'll talk about the classification when you get done with that, but this is the end right here. So number 4 and 5, you may need to look some stuff up here for number 4, and then this is just kind of saying, learn that, because we'll need it later. We'll talk about that when you get there. So focus on filling in these tables, and then we'll talk about it. Yeah, like what have you seen metal before? Experienced metal? So what is it? What is it about metal that makes it? Like if you look at something, you would say, oh, that's metal. What is it that makes that metal that other things aren't?
This would balance out that, you know.
Is this the fan? Which one do you want? Or you doing?
Like if you saw a couple different things, and one of them was a metal and one of them wasn't, what would be the main characteristics? How would you know that one was a metal?
And so,
What other things can you think of metals do that other stuff doesn't? Okay. That's it. Everybody else does. What? No, those are all.
If you don't have to, you just need to dance. Yeah, it's not easy for us, that not with this person. The yellow. Wait, but where did the red go? This question, are you just asking me like how do you know the difference? Like you looking at it?
Yes.
Or you mean like if you did that? How would you know?
Oh, yeah. Like, so
Yeah.
it's not color coded. So if you come up with a way of figuring it out, and you don't have the color codes.
Wait, no. Oh, yeah. The second one, then you said something like.
All right, just getting through this, all right? Like mostly done? All right, well, we'll come back together and we'll talk about some of the rest of it here. Looks like I think everybody's at least getting close to the end. If we go back to these exercises, what are the 4 elements? So we've got 40, potassium 40. What's the next one you came up with? You don't have to tell me the name, but P, phosphorus, okay. And what was this one down here? PR, bromine. All right, so we can fill those in from the periodic table. So for this one, zinc, it's zinc plus 2. That means its atomic number, we look it up, is 30. What's its mass number?
65.
How'd you get 65? 78? How'd you get these numbers? Where'd these come from?
That was the number of neutrons plus
So the number of neutrons is 38 plus 30.
proton. Yeah.
Should be 68, right? 38 plus 30, 68. So when the number of neutrons are specified, then we don't look at the periodic table, we add those together. The mass number is the neutrons plus the protons. We know there are 30 protons because the atomic number is 30. And then how many electrons? Was it 30? It's actually not 30 in this case. Anybody know why? Because of the plus 2, so what should it be instead? Close. 28. This plus 2 up here tells us that there's an imbalance of protons and electrons, and because it's an imbalance on the positive side, that means more protons than electrons. So we've got 30 protons, that means we've got to have 28 electrons, so we have the plus 2. Okay. The other ones all balance out because, except for this bottom one. So should we add something? This shouldn't just be bromine, right? What should this be? What? Well, we can put an 81 in front of it, first of all, yeah. And it should be a -1 because there's one more electron than proton. See that? 36 electrons, 35 protons. So that needs to be -1.
Shouldn't we be the same thing, like -2?
Yes. I didn't see that, yes. So this is 15 and 18. So that should be -3, or 3 minus. These are sometimes written a couple different ways. Sometimes you see the minus first. Sometimes you see the number first. It's generally more common to write the number first. So 3 minus versus -3, just because then it's more clear that it goes with that. It doesn't look like the 3 goes somewhere else. But either way is fine. And then if it's plus or -1, the 1 is usually just left out. It's just the plus or the minus sign. All right, what about classifying elements? How'd you figure this out? How'd you classify them? Did you look up each one and then decide what it was? Yeah. Okay. Is there an easier way to do that when you don't have access to a computer, like on an exam?
Probably.
What do you think?
Probably gradient, right?
Yeah, anybody have any ideas about that?
Different colors in the periodic chart.
The different colors on the periodic chart. Let me switch to that. So there's a nice colored periodic table where we have the metals in blue, the metalloids in green, and the nonmetals in, or semi-metals is another name for metalloids, and then the nonmetals in yellow. But again, we'll have an exam. We might not have a colored periodic table. Is there another way to know?
You have to have a good memory.
You have to memorize every one and then put it where it is?
Where is divide?
Yeah, let's just imagine a dividing line. So you can see in this one, you've got this kind of darkened line here. And in fact, up on that periodic table, you see it as well. You see that darkened line there? So all of the elements pretty much touching this line, except for aluminum, are those semi-metals, or metalloids. Everything over to the right is a nonmetal, and everything over to the left is a metal, with the exception of hydrogen. So that's a pretty good way of of dividing those up. So then one of the things that asks palladium, PD, that's right here, where does that fall? Metal. Right? Everything over here is going to be metals. And then the one on the list that's not either one is germanium, GE, which is right on the line, and therefore is semi-metal. So let's talk about what those categories mean. What are metals?
They're good conductors of heat.
They're good conductors of heat, yes. We talked about that when we looked at the specific heats. They have low specific heats because it doesn't take much energy to heat them all up, so they conduct heat well. What else?
They can be shaped into thin wires.
Yeah, they can be shaped into thin wires or sheets. Anybody ever just hit a car with a hammer?
No.
Good, don't do that. It's not nice to people's cars. But if you hit a car with a hammer, does it just shatter and fall to the ground? No, it dents, right? Or if you hit a car with another car, has anybody ever done that? Then it dents. And that's a property of metals. It's called malleability, or ductility is the wire thing. It can be hammered out into sheets. It can be pulled into thin wires. It can be bent and dented. Non-metals are just the opposite. Anybody know what carbon looks like? Just regular carbon? It's black. It's just kind of like a black, solid, not very interesting looking. Charcoal is primarily carbon. That's a good way to think of. Coal is mostly carbon. And so what happens if you hit that? It shatters. That's a big difference between metals and nonmetals. Nonmetals tend to shatter, and they're very brittle, whereas metals are not. And then the other big difference is conducting electricity. So what happens if you stick some aluminum foil in an electrical socket? Anybody want to try that out? Yeah. Don't try that out. Yeah, because it'll conduct the electricity. Right? The electrons will travel through that piece of metal very easily and with very little resistance and get right to you. That's why we use metals for wires when we're dealing with electricity, because the metals conduct that electricity. Whether it's copper in major wires or just little wires in electronics, metal conducts electricity. Non-metals don't. They're called insulators. They prevent the conducting of electricity. And then the semi-metals, or the metalloids in the middle, kind of have parts of each one. They sort of do both things. They're semiconductors, which means they conduct electricity, but not really well. You kind of have to do special things to them to get them to conduct. That actually makes them especially useful in things like computing. So most of our computer chips are made from silicon and germanium. Other types of semiconductors, LEDs, light-emitting diodes, those are semiconductors. Semiconductors have really changed our lives, and we see them we don't see them, but we use them all the time now in all of these different applications. I guess metals have too, but those have been around longer. So those are the major differences there in these different categories. Any questions about these kinds of things? These kinds of ideas?
Do you have to memorize the name of
Good question. Yes, you have to know all of them. No, you don't have to know all of them. There are a few. I'll post on Blackboard in the objectives for this chapter. I'm not. It might actually be up already. I think it is actually, but the homework needs to be updated. So you can see. I'm probably not logged in anymore here. Oh, there we go. Let's look at it. Yeah, you will need to, but not in this chapter. So it'll be later. You won't need to know all of them. You'll need to know a handful of really common ones.
like on a test, would we just give presentation and
Actually, for tests, and I was looking if we have some here, but I guess we don't have any down here. Upstairs we have a big stack of periodic tables that have the names also. So you'll always have those for quizzes and exams. So you won't need to memorize the names of elements. You will need to know some ions. We'll get into that in another chapter. But mostly you'll have a more detailed periodic table than that. So you'll have the names. It will help, and this will just be something, I don't think this is something you have to study, but as you go through and work on your homework, you'll notice that you start to get a little bit better sense of where things are on the periodic table, because I imagine that's pretty cumbersome right now for you. Like if it says PD, you kind of have to go everywhere to find where the PD is. The more you practice, the more you encounter these things, the easier that will be just to find things. And that'll help speed things up a little bit. But yeah, good question. Other questions about that? All right. Well, let's go on a little bit and talk about electrons for our last bit of class today. The one thing that you've noticed, or maybe you noticed, the periodic table that asked about in the packet is this idea of these families. They go down the columns, and they all have these different names: alkaline metal, alkaline earth metal, halogens, noble gases. They go down this column. Any idea what that means? Why those categories exist? What they're for? What the point is? What? Why do we care that everything in this column is called an alkali metal or this column is called a halogen? What is the similar or even related about these things? Any ideas about that? I mean, maybe it's just that you probably think, well, you guys have stupid names for everything, so maybe it's just more stupid names of stuff. And maybe that's true. But there's actually an important chemical reason for these groupings, that these elements have similar properties. They seem to react and behave in similar ways. And the reason we care about that is not just because it's interesting that these seemingly different things have similar properties, but it allows us to make some predictions about how things will react. So if you have a drug that you want to make a sodium salt of to get it in the body better, and maybe that kind of works, but you want it to be a little bit more ionic, maybe you try potassium instead. You know those are pretty similar, so maybe one can replace the other one and have a similar effect. And that's a lot of how chemistry is done. This type of chemistry is done, where we replace elements with others within that column to try to tweak the properties of whatever it is that we're trying to make. And so these things are called families or groups, these columns. And then the lines across this way are called periods. Why are they called periods? You know? What does it mean for something to be periodic? Yeah. Occasionally, or more like that goes in a cycle. It goes in a cycle. So you've got, as you go from left to right, it kind of repeats itself. So you have similar types of atoms going one after another, or different ones, and then it repeats itself in a similar pattern each time. So that's why it's called a periodic table. Because after you get to this one, you seem to get another element that was just like the one above it. And we're going to talk a little bit about why that is or where that comes from. And the way we do that is by thinking a little bit more about electrons. We'll come back to this. Let's think a little bit about electrons. From this point forward, with one exception in our nuclear chemistry chapter, we're going to focus solely on the electrons. We no longer care what's in the middle of that atom. We talked about it, we talked about isotopes, we talked about nuclei. Great. We're done with that. The reason for that is that no chemistry happens inside the nucleus. The chemistry happens from electrons interacting with other electrons outside of the nucleus. So we're going to focus on those electrons right now. And the thing we're going to focus on is not only counting them, but counting them in kind of a special way. So if we look at hydrogen, how many electrons does a neutral hydrogen atom have? 1. And then how many electrons does a helium atom have? 2. And what about a lithium atom? 3. So for the rest of class, we're just going to go up one by one until we've gotten all of them. No, we're not going to do that. We're going to talk a little bit about how these things are grouped. As it turns out, electrons start changing their energy levels the further they get from the nucleus. Now, why do you think that might be? What is the distance from the nucleus? What kind of effect does distance from the nucleus have on an electron, do you think?
Opposites attract, the further away it is, it would affect on what it's doing.
Yeah.
The further away, that's trying to be closer, maybe?
Yes, you're all the way up until that point. But yeah, the middle of the atom, the nucleus, is positively charged because of all the protons, yeah? And the electrons are negatively charged. So the electrons are pulled into the nucleus. And the closer they are to the nucleus, the stronger they feel that charge. All right? So the further they get away, the more easily they can be torn off and leave and do other stuff because they're no longer pulled as strongly by that force. So it becomes important for us to count these different energy levels in these electrons. So the energy levels look like this. We're going to learn a couple numbers. We'll talk about what they mean. 288. The first level, the closest electrons to the nucleus, there's only room for 2. So 2 electrons can be as close to the nucleus as the first level. Then in the second level, there's room for 8 electrons. And then the third level, there's room for another 8. And there's actually room for more, but we're not going to get into that in this class. So we're going to stick with 2, 8, and 8. What that means is however many electrons an atom has, or an ion, we have to figure out where those electrons go in these levels. Do they all go in the first? Do they go in the first and second? Or the first, second, and third? They always start from the first and go up from there. So hydrogen's 1 electron, which level is that going to be in? Yeah, it's going to be in the first level. And one way that we can express this is on a little graph of energy. We'll make a big E for energy. The closer they are to the nucleus, the lower the energy there is. So I make a little line here. That's going to be my first level. And that's going to fit 2 electrons. And then my next level is going to fit 8. So maybe we'll make a little bucket instead. My next level is going to be a little bit higher in energy, fit 8. And then my third level is going to be a little bit higher still and fit another 8. That first electron that we put in that first level, we'll just make it a little circle here, tells us that hydrogen has 1 electron in its first level. Helium gets 2 electrons. So we can make our same little energy graph with our buckets. And where do the helium's 2 electrons go? Yeah, first bucket. And then we'll move on to lithium. And where do its 3 electrons go? Right, so we're going to put 2 in the first one, and then 1 in the next one that holds 8. So let's label this again. We got 2, 8, and 8 total capacity. We always start from the lower, and then whatever's extra goes to the next level, and whatever's extra after that goes to the next level after that. So now let's jump down and look at sodium, Na. How many electrons does sodium have? 11. And this E with a little negative sign, that's just a short abbreviation for electron. I probably got that. So let's see if we can put sodium electrons in its buckets. Two, 8, and 1. So we go 2, and then we've got space for 8, and that leaves 1 more to get 11 total. See, I told you chemistry was easy. You didn't believe me. All right, so now we've got some models set up here. Let's talk about what this means. In chemistry, when atoms encounter other atoms, they only see the outermost electrons. So the reactivity, or how these things behave around other atoms, is determined by the outermost electrons. And we have a name for those. Those are called the valence electrons. The highest energy electrons that are furthest away from the nucleus, they control the chemistry of any given atom. So in hydrogen, at the very top, what is its valence electrons? There's just one. So right here, this is the valence electron because it's the only one, the outermost electron. If we go to helium, how many valence electrons does it have? 2. What about lithium? Just 1 valence electron. So now in lithium, we can separate these. We call this one the valence electron, and we call these the core electrons. The valence electrons participate in the chemistry. They participate in the reactivity. They participate in interacting with other atoms. The core electrons do not. They're particularly stable, stabilized by that interaction with the nucleus. So what about sodium? How many valence electrons does sodium have? Right. And now all of these are going to be core electrons for sodium. So now, lithium and sodium have pretty similar behavior. They're both metals. They're both pretty soft. Cut them with a knife, like a butter knife. They're both very reactive with air. How can looking at the electrons tell us why lithium and sodium have similar chemical behavior?
Because they have one element at the last. And they're outer.
Yeah, right. They both have 1 electron in their outer shell. They both have 1 valence electron. And actually, hydrogen does too. So we can talk a little bit about how that's similar as well. So what this means is that knowing the number of valence electrons can help you make some predictions about what the atom is going to do. Now, there's a shortcut. You don't always have to draw a bunch of little circles in little buckets to figure out the number of valence electrons. Anybody figure out a shortcut?
I'm drawing the circles and putting the first 2, and then the second 7, 8.
Okay, is that really a shortcut from buckets? It's kind of similar. If you like that better, that's fine. That's fine. What? You could do it in your head. But let's say I asked you how many valence electrons bromine has, Br, number 35. You don't want to draw 35 little circles, 35 little things. Yeah. These might all work, but there's an even easier way. Take a look at the numbers on the tops of the columns. What do you notice that they go up to? 8, right? The highest number on the top of the column is 8. And, coincidentally, maybe, not really, 8 is the maximum number of electrons we can fit in these buckets, in each of these levels, these shelves. So maybe it's set up that way on purpose. What column are lithium and sodium in? 1. And how many valence electrons do they have?
1.
So you see how there's maybe a shortcut? How many valence electrons do you think there are in bromine, Br? If you had to guess, what would you guess? Anyone else guess?
1.
Why 1?
The first shell has 2, and then there are 3 more shells with 8 electrons, and then the last shell has 1. Maybe before the 5.
Okay. That's one way. That's a good way to go about it. That's absolutely the correct way to think about it. Unfortunately, you come to the wrong answer because once we get below the 3rd level, the counting doesn't even work because I'm not telling you some things about the buckets because they're a little bit beyond this class. So we're going to use these numbers instead, and they actually work out. Bromine's in column 7A. Everything in column 7A has 7 valence electrons. Right? Everything in column 6A has 6, 5A has 5, 4A has 4, 3A has 3. The middle ones, the B's, are a little bit weird and don't quite fit, so that's why they get a different letter. But the A's work, and we sure we're for S, number 16, and let's make our graph with our buckets for sulfur. So we've got our 2, our 8, and our 8. And sulfur has how many electrons? 16. So let's count up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. How many valence electrons? 6. Yeah. All right, and it's in column 6A, so it works out. And this is where that issue of the periodic properties, or the ideas that elements have similar properties in the same groups, comes from. They have the same numbers of valence electrons. They're going to have similar chemical behavior. And we're going to learn a little bit about how we can predict some of that behavior based on that. All right, now I also want to talk about, then, some atoms have a particularly stable configuration. Some of them are way more stable than others. In fact, anybody know which ones I'm talking about? Yeah, the ones way over on the right with 8. You'll notice all those elements, those are all gases. They're called the noble gases. They don't really react with anything. We use helium for things like balloons, neon and argon and krypton, and actually all those except radon go ions, neon signs. And they don't really do much reaction. Why do you think that might be? What do you think is special about having 8 electrons in the outer shell there? Is what? They are. So what is it about their electrons that you think makes it that way? Yeah, it's kind of all that. So you've got this, when a bucket is full, there's a special stability there. We can say that the atom is particularly happy when it has a full bucket on the outside. It doesn't want to have these spaces. So atoms that have those full buckets are particularly happy. And those 6 elements are an example of that. Now notice helium doesn't have 8, it has 2, right? But 2 is a full bucket. And there's no more partially filled buckets. So anything with a full bucket is going to be really stable. And that's true for ions as well. So we talked about neutral atoms. Let's go back to ions, which we looked at a little bit in here. For instance, magnesium. Now, how many electrons does a neutral magnesium atom have? 12. And how many valence electrons? 2. Good. So let's make one more batch of buckets. So look at this. So we'll have 2 in the first, 10 or 8 in the second, and then there's 2 left over. All right. Now the most common ion of magnesium is 2+. This is an ion that we see all the time. It's in our body. It's in things like antacids. Magnesium 2+ ion. Now let's do the electron configuration for magnesium 2+. How would that be different? What would the magnesium 2+ or +2 ion have different than the neutral magnesium ion? 2 less electrons. So magnesium 2+ would only have 10 electrons, not 12, right? Because we need to have 2 more protons than electrons. So the 2+ needs fewer electrons. Let's put those in the buckets then. 10. What do you notice that's special about that electron configuration? It's got 8 in the outer shell, or the outer bucket, or the outer ring, or whatever you want to call that. What we would say is the valence shell, or the valence level, is full. And when we know when the outer level is full, that becomes especially stable. So this should tell us that magnesium likes to form a +2 ion to make that stable valence shell. And in fact, that is what happens. Magnesium is a fairly reactive metal. If you, it won't just react too much by itself, a little bit, but have you ever burned magnesium? Have you ever seen that burn? That's what's in sparklers. Kind of gives off a bright white light, gets super, super hot. And magnesium 2+ is quite unreactive. It's used in some processes in our body, but it's pretty unreactive. And that difference is because of the difference in the electron configurations. Magnesium loses its 2 electrons and becomes especially stable. Now, what do you think might happen with calcium then, Ca, which is right underneath magnesium? What kind of ion do you think calcium might want to form? If you had to guess. Why? Yeah. How many electrons are in calcium's valence shell? 2. So that's the same as magnesium, right? So we would predict that calcium would have similar behavior, that it would want to lose those 2 electrons and become a 2+ ion. And in fact, that's what calcium does as well. Calcium is a very reactive metal. They react with oxygen. But calcium 2+ is very stable. That's what we consider like calcium in our food, the calcium that's used to build our bones. Very stable material. So we can make some predictions about how these things are going to react based on their family and based on what happens with their valence electrons. And we'll get into that a little bit more in the next chapter. So, questions?
I still don't understand about calcium. You said calcium?
Yeah.
Okay. Because I'm looking at that one. Okay.
Okay, yeah, calcium Ca, number 20. Let's look at, yeah, we'll get into that later. So that's actually, we're kind of getting into the next chapter. I don't really want to do that yet. So we'll hold off a little bit on that. All right, other questions? No? Everybody's good? All right. Well, let's stop there, just because we don't want to get too much further. I know it's a little early, but if you've got some questions or you've got some other things you want to work on, this is a good time to do that. That one you can keep. Keep that one to study. Yeah, I've got that. I'll have to give it back to you. I think there was a second one. There were two, right? Or was it just? You never turned it in. Yeah, turn in whatever you've got. We won't. I'll give you credit for it for the lab. You don't have to finish it though. The thing last week.
On Monday?
If you didn't turn it in, yeah, on Wednesday. We didn't have class Monday. What? We did another packet like this.
Oh, the one that was supposed to keep. It was in grade, groups of three.
Yeah.
Yes.
Yeah. Yeah, put your names on it and turn in whatever you've got. I'll give it back to you. You don't have to finish it, but then I'll give you credit for it. And you can keep the one from today.